Okay, in this class, first let me give you the problem. Design a gear drive power is equal to 22.5 kilowatts. Velocity ratio is also reduction ratio. Okay, RPM of the pinion is equal to 200. Then approximate center distance uh, 600 millimeter, 20-degree pressure angle stub. Sigma G is equal to sigma P is equal to 60 megapascal. Same material, for gear and pinion. B is equal to 10 times M. Find module. Face width. Number of teeth. Check for dynamic and wear load. Step number 1, center distance is given to us. So that is radius of pinion plus radius of gear. Radius of pinion is module multiplied by number of teeth on pinion divided by 2. Module of gear, number of teeth on gear divided by 2 is equal to 600. You're gonna have 1/2 plus, please note, gear teeth divided by pinion teeth is equal to 1.2 is equal to velocity ratio. So 1.2 divided by 2 M PP. So from here, and M times TP is dP. So you get dP is equal to 400 millimeters, and you get dG is equal to 600 millimeters. Everyone understood this first step? The first step, the center distance is given. What is center distance? Center distance is the distance between the shafts. You have this big gear and you have this pinion. So this is the radius of the gear. This is the radius of the pinion. That should be equal to the center distance. Radius of the gear is the pitch circle diameter, which is module multiplied by number of teeth divided by 2. So we substituted that equation and finally found out the diameter of the pinion, and we found out the diameter of the gear. Second step, we need to find out VP, which is the pitch line velocity. So pitch line velocity, which is pi times diameter of pinion, speed of pinion divided by 60, which is same as pi times diameter of gear multiplied by the speed of gear divided by 60. So VP is equal to pi times the diameter of the pinion is 400, 0.4 times 200 divided by 60. So VP is equal to 4.2 meters per second. With VP, we have to find out the velocity factor, CV. Velocity is less than 12.5. So CV is 3 divided by 3 plus V. So which is 3 divided by 3 plus 4.2. And we get 0.417. Now we have to find out the Lewis form factor, YP, and it goes without saying, since the gear and pinion are of same material, pinion is weaker and will be designed. So YP is equal to 0.175 minus 0.814 divided by number of teeth on pinion. Now at this point, what I want you to do is, I want you to look at the table and tell me the minimum number of teeth that are required on the pinion to avoid interference. And I'm going to say TP is equal to 18. Minimum number of teeth to avoid, I think our interference are 14, right? So YP value is going to be 0.175 minus 0.814 divided by 18, and that is 0.129. Now service factor. Service factor means whether that gear is used continuously or whether that gear is used intermittently, or if that gear pair is subjected to shock loads. So I'm going to assume service factor CS is equal to 1. This is the service factor. And this is assumed.
Have you run into many circumstances where that wasn't the case?
Service factor 1? Yeah, so many a times what happens is they will give you the gear pair is used continuously. Or so for an example, service factor of 1, what it means is usually in 24 hours, the gear utilization or machine is running for 8 to 10 hours. If it is more than 8 to 10 hours, usually that means it's utilized more than the regular service hours. So it's like heavy use, not the normal use. Service factor 1 is for normal use. 1 point up, you can go up to 1.2 if it is continuous used. If it is heavily loaded in a harsh environment, You can go all the way up to 1.3 to 1.35.
So we'd only be looking at higher service level factors if we have like a day shift and a night shift.
Correct. If the machine is continuously used, and this is a very important question, because recognize that you have washers that are made for home use, and you have washers made by the same company for the hotel use, which is commercial use. So if machine is designed for commercial usage, then the service factor would be high, because we anticipate that it would be loaded more. It would be used rough in a sort of a rough fashion. So that's why the service factor is kind of, it's sort of how heavily the machine is used, or what are the operating conditions in which the machine is used. So
Say, for example, we have a situation where half the year we're running just a day shift and the other half the year we're running night and day. What would you?
I would consider heavy. So I would do it 1.2, 1.25. So, and it's completely up to the designer. But there is something else that I want to tell you at here. So, for an example, there's certain, when you look at appliances, or if you look at the consumer goods that are for commercial use and the home use, you can actually have some type of differentiation. However, but let me give an example. Cars. So the manufacturers, they make cars. They don't know if the car that they are making would be used for a rental use, or would it be used for maybe leisure use, or whether it would be used continuously, or it would be used in a rough fashion. So when you design cars, at that time, you always assume that the cars would be severely loaded. The cars would operate anywhere from Alaska all the way to the Arizona. So that's why there are some products that you would always consider them to be heavily used, whether they are heavily used or not. And that is the reason why, if you look at the cars, automobiles, they go for 200,000 miles, because they are so robustly designed, taking into account all the failure modes, failure possibilities, and the rough usage. On the other hand, if you look at the military vehicles, the design principles for the military vehicles are totally different. They are totally designed based on the reliability and the rigidity. So in the consumer products, the design principles are different. And if a vehicle is used in the military applications, the design principles are different. So there are some guidelines pertaining to particular product, pertaining to particular industry. Those design guidelines you have to use. Sometimes there will be some internal data books that they will tell you that, hey, we have to use service factor of this. We have to use service factor of, maybe if that car is used in this type of environment, we have to use this type of service factor. So there are some minor changes, but higher the service factor, that means the machine or the component would be used roughly. So it's not normal operation, it will be heavily used. So with this, since nothing is given to us, I'm just assuming normal operation. Wt is equal to power divided by velocity multiplied by the service factor. Power is 22.5. It's kilowatts, 10 to the power 3, divided by the velocity 4.2 multiplied by the service factor 1. That gives me 5350 Newton. That is the tangential load. Now, with this tangential load, I should be able to find out the module. So Wt is equal to Cv multiplied by sigma O multiplied by V multiplied by pi multiplied by M multiplied by Y. And this value CV, we already know it's 1. In this particular case, we don't have to refer to the data sheet because the value of sigma O is given to us. So if you look at the problem, in this problem, they say sigma G is equal to sigma P is equal to 60. This is nothing but value of sigma O. If this value is not given to us, you are welcome to look at the design data book and select the appropriate value. So sigma O is 60 multiplied by value of B is 10 times module multiplied by pi multiplied by module multiplied by 0.129. And this value is 5350. With that, you should be able to tell me what is the value of module. You can use your calculator and correct my answer. If I'm wrong, I get module of 8 millimeter. Now with 8 millimeter module, now I should be able to find out, please note, the diameter of the pinion is known, dp is equal to module times number of teeth on pinion. Module is 8, diameter is 400. So from here, I should be able to get the value of TP. So TP is equal to 50. And this is fantastic. So one thing I just want to tell you, you cannot have fractional teeth. No fractional teeth. Okay. So for example, you can never have 49.2. You can never have 51.5. Either you have 49 or you have 50. You have 51 or you have 52. So you cannot have fractional number of teeth. And that is the reason why, please note, they give you approximate, this is very important, approximate center distance of 600 millimeters. And that's why they say a stub. Stub means what? The gear top is shaved so that the center distance requirement can be met. Everyone understood this? Yeah.
I just had a quick question. Didn't you assume that the pinion teeth were 18 earlier?
Did I assume?
When you're solving in slide 2?
Oh, yeah, you're right. So where did I assume this? So basically, these are the minimum number of teeth. Nobody has stopped us going above minimum number of teeth.
Okay.
Does that make sense? Okay. Yeah.
Could you also like get module from slide
Yes.
1 and then
Yes. Yes. It will work. See, now you know how to play with design. So that's totally fine. Any other questions from online students or so? Okay. So next part is TG is equal to 800 divided by 8 is equal to 100. Then what I'm going to do is I'm going to check for dynamic and wear load. So check for dynamic and wear load. And you don't have to remember these equations. That's why homeworks and quizzes are open book, open notes. So WT plus 21 V B times C plus WT divided by 21 V plus square root of B times C plus WT. WT is 5350 plus 21 4.2 times. Please note, module is 8. So B, which is 10 times module, is going to be 80. So I'm gonna write equation B as 80. Now C is the correction factor. And for that, I want you to refer to table number. What is the table number for C? And the value of C is, oh, come on, I spent a lot of time talking about all these tables. 80. No worries. Experience is the sum total of all the mistakes. Better make mistakes in class than in industry. Plus square root of 80 times 80 plus 5350. That gives me 10,600 Newton. That is our dynamic load. And at this point, I want everyone to make sure that you are able to get the same value of C as I got. Just quickly look at the table and then find out. Just make sure that this C value makes sense.
Did anyone get the same value of M?
Your value of M is different.
Yeah, it was.
How much is it?
I got 4.7.
4.7. 8 is bigger than 4.7, so design is safe. Oh, I could make. I don't know. Just check my calculations and see if I made a mistake.
What did you get?
I also got 4.7.
Okay.
I'm not going crazy. That's good.
Okay.
It still works. It's still safe. I was just wondering if my value was
Oh,
off.
yeah. I know why you got 4.7. You got 4.7 because I think CV, I made a mistake somewhere. This is not 1. This is 4.17. This is the mistake I made. Don't make this mistake. This is CV, right? This is not CS. Correct? Okay. So now you can divide your 4.7 by 0.417 and tell me what the value you get.
Say it again.
So you got 4.7, right?
And once we corrected that, 8 is.
Okay, 8 is the correct answer. Okay, you're right. So please note my mistake. My mistake was CV is not 1. CS is 1, but CV is 0.417. Yeah, I'm glad you got it. Okay, next, to find static load. Yeah, 80.
in the table. 80.
Okay, you want me to actually walk you through that? Okay.
I just did you have a tooth error interaction value?
Yes. Okay. Okay, what is the page number? 1040. Value of C, the deformation factor. Now, what it is saying is 20-degree stub. Are you with me so far?
Yes.
20-degree stub. Now you have cast iron to cast iron 59, steel to cast iron 81, steel to steel 119. Do you agree with me?
Yes.
Now, here is the issue. In this particular case, the value, the material value is not what we don't know what the material is. So that's why I kind of approximated it to 80. Now, but if you want to be super duper particular, that is totally fine. What you can do is you can use the deformation factor equation, which is C is equal to K times error divided by 1 by EP plus 1 divided by EG, and find the value.
Is it standard to assume the lowest level of error in our teeth? So at 0.01 range.
So no, if you then you have to state what your assumptions are.
Okay.
As long as, so I just use that tooth error in action E, which is the cutter, has the error of 0.01. But if you say that I want to use the tooth error action as 0.02, that's totally fine. So as long as, so what I'm trying to say is, as long as that value is within the reasonable range, it's okay.
Somewhere between 60 and 1,000.
Somewhere between yeah, you're right,
Okay.
60 between 1,000. But if you are super duper particular, and usually in design you don't have to be, I mean, if you are like mathematics type, then nobody has prevented you from using this equation. One divided by EG. So basically K is the factor depending upon the form of the tooth. And let me do this just for one problem, because 115 multiplied by E is the error correction. So what error do you want to use? 0.02. Material is not given to us, but since it's 60, I'm going to assume steel. Okay, assuming steel. What is the Young's modulus for steel? 200 gigapascals, which is 200 10 to the power 6 Newton per meter square. 10 to the giga is 9, sorry, 10 to the power 9. This guy has to be in Newton millimeter, which means this value has to be in Newton millimeter square. And please, if you have any questions, just ask. Okay, there's so much variation in design that I want you to ask me as many questions as you can. So this is going to become 1 divided by EP is EG, EP plus 1 divided by EP. That gives me So EP multiplied by 0.115 multiplied by 0.02 divided by 2. Do you agree with me? And then I will substitute the value here. 200, 10 to the power, this is 3, 10 to the power 3 times 0.115 times 0.02 divided by 2. Now tell me what answer you get quickly.
$230.
230. So you are welcome to use 230. And as you can clearly see, that is in this table. Can you see 0.02, 238 steel to steel? Does that make sense? Online students, did you understand? I just calculated the value. So you are welcome to use 230, but please note this 230 value corresponds to tooth error correction factor or tooth error of 0.02. Okay, but I will continue with the numbers I got. I'm going to find out sigma E is what is the value of sigma E? To find the value of sigma E, you have to go to a table 28.8, and in 28.8 you have various grades, and there is flexural endurance. So you can choose the value, the lowest, maybe lowest value for steel, and say 250. Table 28. And with this, you should be able to find out static load, is equal to sigma E times B times pi times M multiplied by Y, which is 250 times B is 80 times pi times module is 8 times Y is 0.129. And make sure that this load is greater than the dynamic load, and it is. But please just calculate and tell me what this value is.
$64.8 times 10 to the 3.
And the load value here is 10.6. Can you see the dynamic load was 10.6 kilonewton and the static load is 64.8. So which is, I'll just write this down, WD is 10.8 kilonewton, which means design is safe. Everyone understood?
Can we gather a safety factor from that?
You can, but not needed, because the only thing that we have to make sure is our static load is greater than the dynamic load. So next thing, we have to find out the wear load. To find wear load, WW. First, we have to find out Q. Q. Now, this is external gearing. What do we mean by external gearing? That this is something gearing like this. So the equation for this is 2 times PR divided by VR plus 1. So 2 times 2, 2 plus 1, which is 1.33. Now, to find the value of WW, to find the value of wear load, it's always found for pinion. Okay, dP times B multiplied by Q times K. dP is 400, B is the face width 80, 1.33, and now someone tell me what is this value of K. And for that, I want you to look at, there are 2 ways to do it. You can use either table 28.9, use table 28.9 or equation on page 1043, which is this equation. So you can use either of these, and that should I will just use the equation. So sigma ES, that value for steel, you can choose to be 6. I've used 630. So sine 20, 1.4. So which is 2 divided by 200, 10 to the power 3. And that should give you the value of K. And you would find WW, and you will notice your WW is greater than WD. Hence, the design is safe. Yeah.
I was going to say, if you're assuming it's steel, I think it's 350.
350.
The 4th row.
Which steel, right?
Yeah.
Uh,
Unless I'm.
yeah, that's okay. So you wanna recommend BHN of 150? That gives you sigma ES.
I'm getting K equals 0.3.
What, 84.3? 6 sigma ES?
0.3.
No. So value of K, right?
Mhm.
How much is it?
0.3.
And tell me what is the answer you get?
12,800.
12,800, and that is greater than WD, right?
Yeah. which is
10.8.
10 kilometers. Yeah. So yes.
So our gear design is safe. Okay, so next step is shaft design. So in last class, we looked at the shaft I think it was cantilevered. Now I'm going to assume that this gear is simply supported. So this gear is simply supported. So we know the value of WT. The value of WT is 5350. WR is WT multiplied by tan phi, which is 5350 multiplied by tan of 20. And then what I'm going to do is the face. So let's understand this face width is 80. Now I just need to spend a little bit of time on deciding the center distance. So clearly the center distance between the bearings, it depends upon a lot of factors, including the geometry. But unfortunately, we don't know the geometry of the gearbox. So what I'm going to do is I'm going to give you a rough way of estimating the distances. So let's think about, this is 80 millimeter. Now, which means assuming this from here to here, and this is just the assumption, it's same as 80 millimeter, which is same as face width. This same as face width. What I'm going to say is the bearing location is here. The bearing location is here. And the center distance from here to the bearing location I'm going to assume to be 80. This is assume. This distance, center to center, again is 80. So if you were to draw the free body diagram, this is going to look the front view. This is going to look as the top view. This is going to be WR. This is going to be WT. Can somebody tell me what is the value of WR?
Yeah, 200, or sorry, 2 kilonewtons.
2 kilonewtons. WT is 5.3 kilonewtons. This distance is 160. This distance again is 160. Now there are two ways. What I would do is I would find out the moment horizontal and I would find out the moment vertical. So moment horizontal is 5.3 multiplied by 160 divided by 4, which is M is equal to WL by 4 for central span load. M vertical is 2 multiplied by 160 divided by 4. So you get this in kilonewton millimeter. You get this in kilonewton millimeter. So the total moment M is equal to square root of mh square plus mv square. Then we have to find out the torque equivalent. TEQ. So TEQ is equal to square root of m square plus t square. And we know the value of torque already. So is 5350 multiplied by the radius of the pinion. RP is 200 millimeters. So torque is WT multiplied by RP 5350 times 200. So if I were to do 5.3 times 200, I would get the answer in kilonewton millimeter. So I would get the torque equivalent in kilonewton millimeter. Can you quickly tell me these answers?
Momentum horizontal was 212, momentum vertical is 80, momentum in total is 226.5.
Very good. So this is 226.5 square plus one. How much is this?
Or
10
what?
10 kilonewton meter or approximately, or 10.36.
RWR was 2 kilonewtons.
No, WT is 5350, right?
Oh, that's a WT.
Yeah, and RP is 200. So TEQ
It's a really big number.
250.
1,000,000.
1 million square root. Don't forget the square root. There is square root.
I see what you said. Okay. It's about 1,000,000 square, or even with the square root.
226 square plus 10.6 square is getting 1 million.
Oh, I was using my round numbers. Hold on. Uh, 226.
I think it will be a little bit greater than that, but you may have to change the batteries of your calculator. So tau is equal to TEQ divided by J multiplied by R. TEQ is 227, 10 to the power 3 divided by J is pi by 32, D to the power 4, D by 2, and steel shaft. So tau is equal to 45 Newton per millimeter square. So with this, we should be able to find out the value of diameter. And the value of diameter is 226.75. Okay, yeah, so 227, correct. So I was, huh?
That was sent
Before 525. Just he sent, Jacobs just sent this number right now, 226.75 kilonewton millimeter.
I think he said,
Well, it being a kilometer would make sense for the diameter.
Oh, yeah, no, this is the torque, here, the TEQ. This is the value of TEQ.
And you said you need my battery changed.
But that's what I wrote, right? Here 227, no, right? Okay. So Jacob, what is the value of diameter? Tell me real quick. I think it would be about 35, 36. That's just my guess. Going once. Going twice. 3.9. 3.9 for 227 kilonewton millimeter torque. No, 4 millimeter shaft can't sustain that much amount of torque. Okay, I'll let you calculate. And that is how you will do the design for the spur gear. I'll quickly go to the process. This is the start to finish problem for the spur gear design. If you have to design the gearbox, you will have to repeat this process once more for the stage 1 and stage 2. So the steps are: first, depending upon the center distance, we found out the module. Then we found out the pitch line velocity. Then we use the equation for CV. First, we need to find out whether the gear is weak or the pinion is weak. But if the material are same, gear material is same as the pinion material, always design pinion. Then find Lewis form factor, then the service factor. Then what we find is we find WT, and please note this service factor comes over here. So I didn't point that out here. This CS goes over here. Next part, WT is equal to CV multiplied by sigma O B pi M times Y. This is where you will substitute the value of CV. And I made a mistake. I substituted service factor here. That's why initially the module was incorrect. But you need to substitute the CV. CV is for the velocity factor. That is to account for the dynamic or the changing load. We find the module, then we check for the dynamic load. Then we use this equation for dynamic load. Then we find the static load, and the static load can be found out using the equation that is given over here. And for that, we need to find the value of sigma E. That also comes from the table. And then we have to find out the wear load, and we have to make sure that the static load and the wear load, they are greater than the dynamic load. In this particular case, in both the static load and the wear load is greater than dynamic load. Then for shaft design, first and foremost, we have to assume the configuration of the shaft. If it is not given, you are welcome to assume a cantilevered or simply supported shaft. For simply supported shaft, we assume that the load is at the midspan and the maximum bending moment is WL by 4. Find out the moment in the horizontal plane, moment in the vertical plane, find resultant moment, then find out the resultant torque, and then at the end, find out the diameter of the shaft.
Which will be 29.5.
Very good. Thank you. Yeah, I feel good when we actually have the dimensions rather than me just writing the numbers. Yeah, and this makes sense. So 30 millimeter, I said like 36 millimeters. So this diameter kind of, yeah, this shaft would work. The only thing is what you will do, remember, for key weakening, you have to increase the diameter of the shaft. Gear would be keyed to the shaft. So clearly this shaft you will have to make bigger, and it will be about 35 millimeter. Okay, so with this, we finish spur gear design. Are we ready for helical gear design? No? Helical gear design is exactly same as the spur gear design. Can I just write 4 steps for helical gear design and then we'll start. Okay. So what is helical gear? In the helical gear, this is the spur gear. The spur gear, gears are cut along the axis of the shaft. So this is a shaft. In the helical gear, gears are cut at an angle. And clearly, what is the advantage of helical gear? You have more material. Can you see that since you are cutting it at an angle, basically the effective face width is more, which means the gear is strong. So for the same form factor, for the same size, helical gear will transmit more torque. Once again, what is the biggest advantage of helical gear? The biggest advantage of helical gear is for the same size, which is same weight, the helical gear transmits more torque. But what is the problem with the helical gear? Please understand, in helical gear, your load is going to be like this. And when you resolve the load, you are going to have a component of load in the vertical direction, and you are going to have a component of load in the horizontal direction, which means in helical gear, you are going to get axial load. So in spur gear, you can just use the rolling contact bearings. In helical gear, you must have a thrust bearing or thrust bearing. So here you can get away with radial bearings. So in helical gear, you get this side load. So in helical gear, there is something called as axial pitch, which is distance between similar faces on adjacent teeth. And you have something called as normal pitch. In normal pitch, distance between similar faces perpendicular to helix. And the equation normal pitch is equal to PC multiplied by cosine alpha. And one thing, please note that now face width B is going to be 20 to 30 times module. So in spur gear, the module to face width ratio was about 10 to 14. But in the case of helical gear, the face width to module ratio can go from 20 to 30. That's why you will see the helical gears, they are stronger compared to the spur gears, because you just cut at helix and that gives you more material. Procedure for helical gear is exactly same. Step 1 is to find out WT. Step 2 is to find out CV and module. Step 3 is to find the dynamic load. Step 4 is to find static load. Step 5 to find the wear load. And step 6 is shaft design. And the equations that we are using for spur gear, similar equations are to be used for helical gear. As a matter of fact, the tables that we are going to use for helical gears are same as spur gears. But what we would do is, we would actually first find out the equivalent number of teeth, which means for if we come up with maybe n number of teeth for helical gear, from those helical gear teeth, we have to find out the equivalent number of teeth for spur gear. So in helical gear, we have to find out TEQ, which is T divided by cosine cube alpha, where alpha is the helix angle. So if your helical gear has 10 number of teeth and the helix angle is 15 degrees, you will take that 10 divided by cosine cube 15 will be the number of teeth on equivalent spur gear. So step 1 is to take that helical gear, convert that helical gear into equivalent spur gear and follow the design procedure for spur gear. 4 steps. And what I would do is, I would discuss those steps. I will give you the helical gear nomenclature, addendum, dedendum, addendum circle, dedendum circle, various ratios. Then I will give you the design recipe. There is not much theory to discuss in helical gear, because idea is take the helical gear, convert that into spur gear and use the equations for spur gear, equations and tables for the spur gear, and get done with it. So next class, I will give you the step-by-step recipe for helical gear and I'll work out the problem. I'm going to stop here. If there are any questions, I would be happy to answer.